Hello friends, welcome back to this series on statistical mechanics, where we try to derive the physics of macroscopic systems from the underlying microscopic processes that govern their constituents. This is the third lecture. In the last lecture, we have focused on applying the Boltzmann distribution from lecture 1 to the ideal gas. In particular, we have derived the ideal gas law and the average energy of the gas, as well as proving the famous equipartition theorem of energy, which says that the average energy carried by each degree of freedom of the system must necessarily be equal under thermal equilibrium. And we have done this under pretty general assumptions about the Hamiltonian of the system. For all these applications, we noticed that the log of the partition function kept showing up, for instance in calculating the pressure and energy, and much else, as we shall see further in this series. Basically, most of the statistical properties of the system under thermal equilibrium can be calculated by taking the appropriate derivatives of log z. This function has an important place in statistical mechanics. Multiply this by the negative of kbt, or the inverse of beta, is what is called the free energy, or the Helmholtz free energy to be more specific, after the German physicist Hermann von Helmholtz. This is an example of what is known as a thermodynamic potential. This function has far more marvelous uses than for calculating pressure and energy, as we shall see. The next topic we will cover is on the method of Lagrange multipliers. This is a powerful tool for optimizing functions with respect to its parameters in situations where the parameters are under constraints and are not allowed to vary in an arbitrary way. Problems like this frequently occur in statistical mechanics. For example, take the free energy. This form here is only valid for the system under thermal equilibrium. In a moment, we shall introduce a form which also applies to a system out of equilibrium, assuming that this system can be described by a set of probabilities at any instant. We will show that F is minimized as the system approaches thermal equilibrium with the probabilities pi's as variables. More specifically, we shall minimize beta f with respect to pi's with the constraint that the probabilities sum to 1. As we shall see, this constraint can be implemented by adding to beta f such a term. This lambda is a new variable, which is what we call a Lagrange multiplier. The problem is then transformed into minimizing this new function, and this is the key. The variables pi's and lambda can now be varied in an arbitrary way, like the usual way we take derivatives, without having to implement the constraint in an explicit way. Why this works shall be explained in a minute, but the result is that we get the Boltzmann distribution as the minimizing solution. That is, the probability approaches the Boltzmann distribution at thermal equilibrium. This can be seen as an alternative to the derivation we have presented in the first lecture. The last topic in this video is on quantum statistics. We have already covered a bit of this in the last lecture when we talked about identical particles, specifically about how in quantum mechanics, particles of the same type are basically indistinguishable due to the lack of well-defined particle trajectories. For instance, if we label two particles by 1 and 2 at some initial time, the particles would have to follow some kind of trajectories over time so that we could label them in a consistent way at later times. Without such trajectories, particles can only be labeled by their measured quantum states at any given instance. This naturally leads to the question, what sort of quantum states would describe multiple identical particles? The answer to this, which we shall study in some details here, will give us two types of solutions. The first corresponds to particles called bosons, and the second type, fermions. Bosons are particles that can occupy the same state as each other. While no two fermions can occupy the same state, we shall study the statistical mechanics of such particles. But before that, let's first go through the exercises from the last lecture. If you'd like to skip ahead to today's topics, use the timestamps in the description below. If not, let's begin. The first exercise is about normalizing a Gaussian wave packet. This wave packet is built from the superposition of plane waves with a Gaussian momentum distribution. In the last lecture, you were asked to find a constant n, such that the normalization condition is satisfied. To do this, we must first find the wave function psi tilde by calculating the integral in the blue box. We can simplify the form of the Gaussian function by changing variable this way. It is now straightforward to apply the standard identity for Gaussian integrals in the yellow box, which can be derived by completing the square in the exponential, making the appropriate substitutions for the parameters a and b. The integral in the blue box is easily solved. Now for the exponential term. Simplifying this factor in front. And we have the position space wave function psi tilde. Now we are ready to integrate over its absolute square. Notice that the plane wave is eliminated. We have assumed the factor n to be real. Once again, we can use the Gaussian identity to solve the integral in the blue box. This is won by the normalization condition. This gives us n. And we have the answer to our question. Let's simplify this. Thus we now have the normalized wave function in position space. As discussed in the last lecture, this can be written as the bracket between the position state and the state psi p naught. Let's express this in the earlier integral form. The first term under the integral is the plane wave, or the momentum wave function, which means the second term is the wave function of the state psi p naught, but now in momentum space. This is so because we can view the whole integral as the insertion of the identity operator in momentum basis into the bracket that defines the position wave function. Now we can compare the position space wave function with its momentum counterpart. They are related by the integral relation below, which is basically just a Fourier transformation. Since the position space wave function is normalized, this means the state vector psi tilde itself is normalized, which naturally implies that the corresponding momentum space wave function is also normalized. Here we have verified the well-known fact that a Gaussian function turns into another Gaussian by Fourier transformation. Let's compare the spread of these two Gaussians. We can put the position space wave function into a form similar to its momentum counterpart, with delta x as a spread in position space, which is defined in the blue box. This equation relates the position spread of the particle to its momentum spread. Let's rewrite the constant factor in front and use the relation in the blue box. Now the similarities between the two Gaussians become even more apparent. The equation in the blue box is just a special case of the famous Heisenberg's uncertainty relation. In fact, it saturates the inequality. This means the Gaussian wave function describes a state of minimum uncertainties shared between position and momentum. Since we are talking about wave packets, let's see how they evolve in time. Classically, this is how light waves propagate. The angular frequency is related to the wave number by a linear dispersion relation, where c is the speed of light. If this is a wave function, we could derive this from how a quantum state evolves in time. We have discussed this in the last lecture. If this wave packet describes how a particle is localized, then we could maybe relate the motion of the wave to the motion of the particle itself. And this will allow us to figure out exactly what the Hamiltonian operator should be. In the last lecture, while we have defined this as a Hermitian operator that generates time evolution in a quantum system, we stopped short of providing a prescription for this operator. This discussion will fill that gap. Note that the insight is this. If we view the wave packet as the wave function of a particle, and if this is observed at a low enough resolution in space, such that the wave function does not collapse into a smaller region, then this wave packet should seem to us to move like a classical particle, with the center of mass of the packet tracing out a definite trajectory, according to the familiar laws of classical mechanics. This is sometimes called taking the classical limit. You can find out more about this in Lecture 4 of my series in Quantum Mechanics. See the link in the description. Let's assume a general dispersion relation, where omega is some function of k. Furthermore, assume that the distribution in wave number be very narrow and concentrates around a particular value k0. This means the spread delta k is very small. This suggests that the momentum of the particle is approximately h bar k0. If we now expand omega k around k equals k0, the higher order terms could then be neglected, since these are only significant for large deviation from k0, but in this situation, gk will be small. So the wave function is mainly built out of the superposition of plane waves with k close to k0. This coefficient of the linear contribution, which is the derivative of omega with respect to k evaluated at k0, is called the group velocity of the wave packet. As we shall see, this group velocity corresponds to the average velocity of the wave packet. Let's split this plane wave into two parts, such that one of them is independent of k and can be brought out of the integral. We want to put all the k dependents as k minus k0, since the function gk is centered at this value. Notice that the term in the red box is the wave function at initial time t equals 0, with x minus vgt in the position argument. Except for this extra plane wave in front, but these phase factors will not matter when we calculate probability density. From this, we have an equation telling us how the probability density over position space changes with time. Basically, the wave packet is translated along the x-axis with velocity vg. This is why we call it the group velocity of the wave packet. More accurately, the width of the wave packet should spread out over time due to the initial uncertainty in its momentum. But due to our earlier assumption of this uncertainty being small, this effect is neglected. This group velocity can then be equated to the central momentum of the particle divided by the mass of the particle. The derivative of omega with respect to k can be written as the derivative of energy with respect to momentum, according to Planck's and de Broglie's equations. Thus, we have a differential equation relating the energy of the particle to its momentum. The solution is nothing but the non-relativistic kinetic energy of a particle traveling freely in space. If we identify the Hamiltonian as the operator that represents the energy of the system, H can then be constructed out of the momentum operator in exactly the same way. And it follows that the momentum states are also energy eigenstates for this particular example, with eigenvalues that match those in the red box, which correspond to the appropriate oscillation frequencies for the wave packet. To justify our assumption that the Hamiltonian that governs the time evolution of our quantum system is really its energy, we just need to equate the wave packet to the time-dependent wave function in position space, then make the time evolution due to h explicit. If we select the initial state appropriately, this is the obvious choice. We can reproduce the wave packet above. This prefactor is to cancel the normalization factor of the momentum wave function. Applying the Hamiltonian in the green box on the momentum state P, we have Now substitute in the yellow box. Here we change variable to k. And indeed, we could reproduce the time-dependent wave packet from quantum time evolution as long as the energy of the system is prescribed as its Hamiltonian. Although in this example, we are describing a particle moving freely in space, this rule can easily be generalized to the case with interactions. For example, we could include in the Hamiltonian the potential energy of the particle when the particle is moving through an external field. In other words, we simply identify the Hamiltonian of a system with its total energy. The second exercise has to do with a more general form of Gaussian integral. We encounter this while trying to calculate the partition function of a system with m quadratic degrees of freedom. The energy of the system consists of terms where different degrees of freedom couple with each other through the matrix A in a quadratic way. This matrix is symmetric and has positive eigenvalues. Our task is to evaluate this partition function and calculate the average energy of the system. The key is to notice that this integral can be put into a form of an ordinary Gaussian integral by an appropriate change of variables. The entry point to this is based on the well-known fact about symmetric matrices like A. A can be written as a diagonal matrix multiplied by a matrix O on both of its indices. The diagonal entries of this matrix are just the eigenvalues of matrix A. O has the property that contracting two of them by an index gives a Kronecker delta that carries the remaining indices. Or to write this in a more familiar form of matrix multiplication, we have O times O transpose gives the identity matrix, which means O is an orthogonal matrix. We say that the matrix A is diagonalized by O. It is a well-known fact that all symmetric matrices can be diagonalized this way. One obvious fact that we have assumed up till now is that A and the other quantities are all real. This stems from the fact that the energy E is real, as well as the variables Q. Now we substitute this expression back into E. Now we transpose both of these O's such that these look like matrix multiplications, just to make them easier to read. These two terms quite naturally tell us what variables we should change to. The new variables are now all decoupled from each other. This is the form of a standard Gaussian. This result is entirely expected and is the reason why we diagonalize the original matrix A in the first place. The coefficients to Q bar square, the AKs, are the positive eigenvalues that we have mentioned before. And the reason why they must be positive is now clear. This is so that the Gaussian integral will converge. This is the same point made in the last lecture. Now we need to work out the integration element in terms of these new variables. That is, we need to calculate the Jacobian of the transformation. This result turns out to be trivial. The Jacobian matrix is the partial derivative of the new variables with respect to the O, and this is just equal to the matrix O transpose. Since O, and by implication O transpose, are both orthogonal matrices, this implies that the Jacobian, which is the determinant, must be equal to 1. This is easy to see by taking the determinant of the orthogonal condition. Thus the integration element is unchanged by the change of variables. When this expression of E is substituted back into the integral, it simply factors into m Gaussian integrals. Each of these can be solved by the standard identity. Since what we want is to calculate the average energy, we are only concerned about how log z is dependent on beta. While all the variables that are not dependent on beta are collected into the parameter tilde alpha, which we can ignore. Using the equation above, we can see that each quadratic degree of freedom carries the same energy on average, half kBt. This is the equipartition theorem. In this exercise, we have shown that this theorem applies even when the energy of the system takes a more general quadratic form. We now get into the first topic of our lecture, the free energy. This form, which is for a system under thermal equilibrium, has great practical applications, as we have shown in the last lecture, due to the fact that it has the form of log z, making it a convenient generator of the thermodynamic quantities of the system. Another way to look at this expression is if you take e to the power of minus beta f. This is just equal to the partition function z. I find this much easier to remember. Recall that beta is just 1 over the Boltzmann constant times temperature. We now claim that the expression for F in the red box can also be written as the average energy minus T times S, the Gibbs entropy. This is under thermal equilibrium, so the probability is given by the Boltzmann distribution. This is what we will show if we substitute the PIs in the blue box into the expression in the green box. We will recover the red box. But please note that the expression for F in the green box is actually more general, and is applicable even to systems that are out of equilibrium, but can still be described by a set of probabilities at any instant in time. We define this F as a function of the probabilities, which is not necessarily the Boltzmann distribution. We shall come back to this in a moment. Now let's substitute the blue box into the green box. First do the substitution on this log term. Notice that these two terms cancels, and we are left with this sum of probabilities is just 1. Thus, indeed, the expression in the green box is another way of expressing the free energy at thermal equilibrium. This new form for the free energy is related to the following important question. What is the most probable macro state of a system at thermal equilibrium? For instance, we could ask what is the most probable energy a system could have. To answer this question, we simply have the sum over all the probabilities from the Boltzmann distribution that corresponds to the same energy. These correspond to all the states in a microcanonical ensemble with the same energy E. All these states must necessarily have the same probabilities, and thus the total probability is just the number of microstates omega multiplied by the individual probability. We can simply ignore the 1 over z since it is just an overall normalization factor and irrelevant to our purpose. Now write everything in the form of an exponential. I think you can see where we are going. This term is just a familiar Boltzmann entropy, which is just a special case of the more general Gibbs entropy. It is apparent that minimizing this term in the exponent with respect to energy will give us the maximum probability and answer our question above. This expression corresponds to the free energy of a microcanonical ensemble and has an identical form to its counterpart above, which is the free energy of a canonical ensemble. Thus, the most probable energy that a system could have under thermal equilibrium corresponds to the minimum free energy. This is why many problems in statistical mechanics and thermodynamics involve the minimization of the free energy. Now let's go through an important example of such a problem. You'll see that with only simple arguments, we shall prove that there is no one-dimensional ferromagnets. There's a model that is often used to describe magnetic materials. This is the Ising model. In this example, we are only interested in the one-dimensional version. This is a 1D lattice with a spin on each side that is labeled by the index I. We have assumed that there are n sides in total. These spins can only have two possible orientations, up or down, along a chosen axis. The spins are carried by the electrons on the lattice sides, and being spin half particles, the projection of their spin along any axis can take only two possible values. The reason why a given axis is preferred has to do with the properties of the material. More precisely, this is due to the spin-orbital coupling between the spins and the distribution of electronic charges in the material. Since we are only trying to illustrate the use of the free energy, these details are not that important. All you have to know is that the dynamical variables of our system are the set of spins SI's, and they each can only take two possible values, +1 for spin up and -1 for spin down. These spins represent the magnetization of the material. And this is the Hamiltonian of the Ising model. The first term describes how each spin at their respective side interacts with an external magnetic field. This field is denoted by little h. In general, it could be non-uniform, hence its index. The second term is the interactions between pairs of spins in the material. J is the coupling strength of the interaction. In general, this will depend on the separation between the two spins, hence J is a two-index object. Both H and J are real parameters, and these interactions are derived from the magnetic interactions of Maxwell's electrodynamics. They represent the interactions of magnetic dipoles with an external magnetic field and between themselves. We have moved the minus sign to the Hamiltonian because there is also a minus sign in the partition function. This way we don't have to always think in terms of double negatives. Just a small convenience to make thinking easier. The trace TR is just a short form for summing over all the configurations of the dynamical variables. This is a standard convention. Why we have a negative sign in the Hamiltonian in the first place has to do with another convention. This is so that a positive J coupling will correspond to a ferromagnet. This will be clear in a minute. This defines the generic form of the Ising model. Notice that at this schematic level, we have not made any explicit reference to the dimensionality of the lattice. In fact, this form of the Hamiltonian can also be used for a higher dimension lattice. Now we specialize to the simpler case of uniform field and coupling. This is the Hamiltonian we shall often use when discussing the Ising model. For example, we want to show that in the absence of an external magnetic field, there could not be an ordered phase like the ferromagnetic phase, where all the spins are pointing in the same direction, if the temperature is above absolute zero. And for the coupling between spins, let's make a further simplification. Let's assume that the interaction is short range, so only the couplings between the spins that are nearest neighbors on the lattice are non-zero. We implement this by summing over just pairs of sides that are nearest neighbors like these two. And this is notated by an angle bracket. At zero temperature, we claim that for J greater than 0, the material will settle into a ferromagnetic phase where all the spins are pointing in the same direction. These two are the ordered phases. We can easily show that their corresponding free energy has the minimum value. At t equals 0, the entropy term may be dropped, and F is minimized by just minimizing the energy. It is easy to see from the Hamiltonian that this is just the negative of the total number of nearest neighbor couplings, which is n-1 times J. This is precisely the energy of the two configurations above. Often, we shall assume the thermodynamic limit, where n goes to infinity, so it doesn't matter if we write n-1 or n, just the same order of magnitude will do. So at zero temperature, ferromagnetic phases are possible as they minimize the free energy. On the other hand, when the coupling J is negative, we have what is known as the antiferromagnetic phases, where the spins are staggered, like these two configurations. They have the same energy as the ferromagnetic case for the same magnitude of J. Since the energy due to each pair of spins remains essentially the same, because we have a minus sign due to anti-parallel spins, which is cancelled by the minus sign of J. These configurations are also considered to be ordered phases because of their regular ordering. The precise value of J depends on the microscopic details of the material. In this example, we will just stick with the ferromagnetic case. What happens if the temperature is greater than 0? Would such ordered phases still be favored by the free energy? Let's just focus on one of these configurations. Is this configuration stable against thermal fluctuations? That is, does it minimize the free energy? And what do these words mean? Fluctuation means, instead of a definite configuration, we have a probability distribution. And this is due to the thermal interaction between the system and its environment. And a configuration is stable against fluctuations if it has a very high probability of occurrence. This is indicated by a minimum free energy under thermal equilibrium, as we have shown earlier. For the case of non-zero temperature, the minimization of the free energy is now a competition between the energy of a macro state and its entropy. If this configuration really has the minimum free energy, then any perturbation from it will increase its value. Let's consider the smallest perturbation. What about this? Flipping one spin. What is the change in free energy? The change in E comes from flipping the sign in both the couplings attached to the spin being flipped. Each results in an increase of 2J. As can be seen from the Hamiltonian. While the change in entropy comes from the number of ways to flip one spin, which is n. This is actually not the smallest way we could disturb the original configuration. We can do this in a way that change only one link instead of two. Like this. This way, the energy increases only by 2J. While for the entropy, the number of ways to introduce such a wall is just n-1. Such a wall that separates the spins pointing in opposite directions is known as a domain wall, and the regions with same spins are the magnetic domains. Notice that if we take the thermodynamic limit, the change in entropy will be dominant in the free energy for any temperature that is not 0. And this means delta F will be very much less than 0. Which is to say that even the smallest perturbation on the ordered state has a very much lower free energy than the original state. Thus the ordered phase is infinitely unstable in the thermodynamic limit and could not exist. Thus we have proven that the ferromagnetic phase cannot exist at temperature above 0 for a one-dimensional lattice. This result is due to Lev Landau and Rudolf Peierls and is an excellent example of the use of the free energy. Now let's go back to the expression for the free energy mentioned earlier. As we have said, this is a definition that holds for any arbitrary probability distribution that describes the system. Not just under condition of thermal equilibrium, but even for systems that are out of equilibrium. As long as they could be described by a set of probabilities Pi's at any instant in time. Taking lessons from what we already know about the free energy during thermal equilibrium, what sort of probability distribution will result from minimizing this form of free energy? Let's find out. Note that since the pi's are a set of probabilities, they must sum to 1. Thus this minimization must be done under a constraint. There's a general technique used for situations just like this. This is the method of Lagrange multipliers. It is a method for solving such optimization problems under constraints. Let's see how it works with this example. Let's bring beta to the left-hand side of the equation. Let's minimize beta f, which is a dimensionless function, with respect to the pi's, which are also dimensionless. Thus, the first order variation of f with respect to p must be equal to 0. Note that delta pc is the variation with respect to the pi's while maintaining the constraint. We need to solve this equation for the probabilities. Let's transform this problem into a simpler one, where the variation can be done freely, like usual, without imposing any constraints. We can do this by defining a modified free energy, F tilde, which is just the original free energy with an additional term. This term in bracket is from the constraint, and its coefficient is what is known as a Lagrange multiplier. We should see it as an additional independent variable of F tilde. Notice that the first order constraint variation of this new free energy is just equal to that of the original free energy, because the constraint variation of the constraint function is just 0 by definition. So if we want to find the probabilities that minimize f and satisfy the constraint, replacing f with f tilde is the equivalent problem. But the point is to switch out the constraint variation with an unconstrained one, varying even the new variable lambda. Let's see how this works. First, let's give the constraint function a generic form. When c of p is set to 0, we have the constraint. This allows our discussion to be more general, as we won't be using the explicit forms of the functions involved. Now we vary f tilde with respect to all its variables independently, and minimize the function. Delta f and delta c in the red box are both variation with respect to just p's. Since delta p and delta lambda are independent variations, their coefficients must be equal to 0 in order for the arbitrary variation to be 0. This leads to two sets of equations. The first set of equations are from the variation of the pi's, so there's one equation for each probability. And the second is from the variation of the Lagrange multiplier, lambda. This just reproduces the constraint equation. The constraint equation is now a condition for the vanishing of the first order variation with respect to a new variable, instead of something we have to impose separately. There are just the right number of equations for the given number of unknowns, so these equations ought to be solvable. Solving the first set, we have the probabilities as functions of beta, which is the temperature parameter, and lambda. These probabilities are not yet normalized. The purpose of this lambda is to help satisfy this constraint. The constraint equation can be used to express lambda in terms of beta. When this is substituted into the pi's above, we would then have the solution to all the equations. We now show that this is in fact also the solution to our original problem. The key point to note is that this solution is normalized for any value of beta. Therefore, we could implement the constraint variation through the variation of beta in the probabilities. This variation is taken around the beta value that is set as a parameter in the problem. And as we have shown earlier, f tilde and f are equivalent under the constraint variation. And since our solution satisfies the equation at the top under any arbitrary variation, which includes the constraint variation of both the p's and lambda through beta, this means this equation is also true, which implies that this equation is satisfied. This is just the original problem we are trying to solve. Thus, we have shown that our solution to the unconstrained variational problem with the addition of a Lagrange multiplier is also the solution to the constrained variational problem. The key point of the method of Lagrange multipliers is this. An unconstrained variation is always easier to carry out than a constrained one, and by introducing extra variables, we are able to implement this idea. Let's solve this equation with the explicit expressions of f and c. C is given by, and the derivative with respect to pi is just 1. And from our general expression for free energy, this term evaluates to solving this for pi, we have, and summing over I to impose the normalization constraint. We could solve this for lambda. Notice that this term on the left-hand side is just a partition function. Substitute this back into the probabilities. Let's note the dependence of lambda with respect to beta explicitly. This is just the Boltzmann distribution, which is the distribution at equilibrium. Thus, we have shown that a system evolves towards the minimum free energy to reach thermal equilibrium. So whether or not the system is in thermal equilibrium, it tends towards an ensemble that minimizes its free energy. Let's quickly check if the Boltzmann distribution does indeed minimize the free energy. Its second derivative being positive implies that f is really minimized. Let's summarize the method of Lagrange multipliers. We are solving for a set of functions pi's such that the constraint variation of f is 0 to the first order. We then convert this problem into one that involves the unconstrained variation of some modified f tilde, which has an additional variable lambda, a Lagrange multiplier. This second form is usually easier to solve and would have solutions that satisfy both the original equations and constraints. Note that in general, given m constraints, we would just introduce a Lagrange multiplier for each constraint in a similar way. Our arguments carry over to this general case directly. We have discussed the free energy for both the equilibrium and the non-equilibrium conditions, as well as for the canonical and the microcanonical ensemble. And the free energy basically took the same form in all these different situations. This is the expression to remember. Here's an exercise for you to get some practice on Lagrange multipliers. Feel free to skip ahead using the timestamps in the description if you are already familiar with this method. If not, let's begin. Your task is to maximize the entropy with respect to the probabilities. This is equivalent to maximizing this dimensionless function. And do it under these constraints. First, the average energy is fixed at some constant value. The second constraint fixes the average particle number. And the third is the usual normalization constraint. Now our task turns into maximizing this modified entropy. Beta is here treated as a Lagrange multiplier, which will fix the average energy, while mu is another multiplier that fixes the average particle number. Lambda, as before, normalizes the probability. Show that this leads to the Boltzmann distribution for the Grand Canonical Ensemble. The answer will be revealed in the next lecture. We have reached the last topic of today, which is the quantum statistics of identical particles. Recall that we have briefly mentioned this topic in the last lecture while discussing the ideal gas law. We shall see in a concrete way why identical particles are really indistinguishable in quantum mechanics. The relevant states involved are the multi-particle quantum states, psi-i's, where I index all the possible states that a system of particles could take. It carries the relevant quantum numbers, E the energy, and N the number of particles. Let's assume that the system is in thermal equilibrium with its environment and could exchange with it both energy and particles. Then the appropriate distribution that describes these states is the Boltzmann distribution for a Grand Canonical Ensemble, which we have derived in the first lecture. Why we choose the Grand Canonical Ensemble, where the number of particles in the system may vary, is just a matter of technical convenience, as we shall see in a moment. There's another way to describe a multi-particle state, which is much simpler when we are talking about a system of identical particles. If we make the usual assumption that at thermal equilibrium, the interactions among the particles are weak enough such that their total energy is simply the sum of all their individual energies, then we may describe a system of identical particles by a spectrum of single particle states, together with the number of particles occupying each state. We call this set of numbers occupation numbers. The subscript i index the single particle states psi-i. These states are energy eigenstates with eigenvalues epsilon i's. Let's assume that the number of such states are arbitrary, maybe infinite. So given this set of single particle states, we can simply describe each multi-particle state by a set of occupation numbers. Let's write the partition function of the Grand Canonical Ensemble in terms of single particle states and their occupation number. Using the green box above, the exponent of the Boltzmann weight can be rewritten as, while the sum over multi-particle states can be written as the sum over the occupation numbers of all the single particle states. Since the term in the exponent is the sum over all the single particle states, the exponential can thus be broken into products along this line, and so can the entire sum. This can be written neatly as a product over all the single particle states, which we have assumed could be an infinite number of them. We can see this term in the red box as a partition function associated with a single particle state. Let's denote this as Zi. This partition function will capture all the details of the quantum statistics of identical particles. We shall see that there are two general categories of particles known as bosons and fermions. Their difference lies in the number of particles that can occupy the same single particle state. For the bosons, many particles can occupy the same state. There are no restrictions. While for the fermions, there could be at most only one particle that can occupy any given state. This is also known as the Pauli exclusion principle. Whether a particle is a boson or a fermion depends on its intrinsic spin if we are talking about an elementary particle. Particles of integer spins obey the boson statistics. For example, the photon, which has spin 1, or the famous Higgs boson, which has spin 0. And particles of spins that are half integer, for example the electron, which has spin half, obey the Fermi statistics. The connection between spin and statistics of an elementary particle can be derived from the formalism of relativistic quantum field theory. But that is a topic for another video. The particle statistics themselves follow directly from the description of the quantum states of identical particles. This we shall cover in a moment. Let's first look at the difference between the statistical mechanics of bosons and fermions. Let's calculate Zi. For bosons, this sum goes from 0 to infinity, and we simply have an infinite geometric series, which has this standard result. This series converges only with the assumption that the exponential factor in the denominator is less than 1. We shall see why this makes sense in a minute. For the case of the fermion, there can be only two terms in the sum. Thus we have the result for Zi for both bosons and fermions, and consequently for the full partition function Z. It is apparent that they are quite different. The full partition function Z is simply the product of all the partition functions of each individual state. Now, if we look at the probability for the system to be in a particular state, as in the blue box above, the Boltzmann weight associated with this state is also the product of all the contributions from each individual single particle state. This is the direct consequence of the total energy being just the sum of the energies of all the particles. As a result, this probability can also be written as the product of probabilities associated with each single particle state. Looking at a representative term, isn't this just a probability for a system to have Ni particles when only one state, psi I, is available to the system? Note that these individual probabilities are already normalized, and we have not specified the range of the summation explicitly, so that our results can be applied to both bosons and fermions. Let's calculate the average number of particles that can be found in a single particle state I. Using the probability above, we have, apart from the sum associated with state I, all the rest sum to 1, and we are just left with, which is just the average number evaluated with the probability Pi, an expected result. And from the definition of Pi in the white box, this is just the derivative of the log of the partition function Zi, dividing out the extra beta. Once again, we see that log Z is more directly involved when calculating thermodynamic quantities. Now we can plug in our result for Zi from earlier. Log Zi for bosons, and for fermions. As we can see, the two cases differ simply by some signs, and can easily be combined into a single expression. The upper sign is the boson case, and the lower sign, fermion. Using this to calculate the average particle number in state I, we have This is the average occupation number of a single particle state for a system of identical particles under thermal equilibrium. This is an expression worth remembering, as it condenses both the boson and the fermion case in a single expression. The two differ only by a sign in the denominator. It can be applied to many situations involving identical particles. All we need is the spectrum of single particle states available to the particles. We shall see many examples of its application in this series. For now, let's note the key difference between the two cases. For the boson, the average number of particles in a given state is only limited by the value of the chemical potential μ. In principle, it could go to infinity, as the exponential term in the denominator approaches 1. Note that this exponential in the denominator must be greater than 1, since the average particle number can only be non-negative. This is consistent with our earlier condition required for the convergence of the partition function for bosons. For fermions, no such condition is necessary. The maximum average number of fermions in a state can only reach 1, as the exponential term is minimized at 0. This is consistent with the Pauli exclusion principle. So far, so good. Now we shall explain why we specifically chose the Grand Canonical Ensemble to describe our system. Using the result above, we could calculate the average total number of particles by summing over the contributions from all the states. Notice that we could fix this average number with μ, which is still an undetermined parameter in the probability distribution. Thus we could see μ as a Lagrange multiplier that fixes the average particle number. In fact, this is in the exercise we have introduced earlier. μ is just another way of expressing particle number through this equation. Note that this is a lot simpler than using the canonical ensemble for our partition function, and then demanding that the total number of particles over all states must be fixed to a constant value whenever we do any summation over particle numbers. This is the key reason why we choose the Grand Canonical Ensemble in the first place. In the next lecture, we shall give a simple reasoning that will demonstrate the equivalence of all the statistical ensembles under thermal equilibrium if we take the thermodynamic limit. From this perspective, the choice of ensemble is just a matter of convenience, like what we just did. Now, let's get back to the question of how the quantum mechanics of identical particles leads to their statistics. Let's start with just two identical particles. How do the quantum states of such a system look like? Since we know how to describe the quantum state of one particle, which is a state vector, or ket in Dirac's notation, a two-particle state is just two kets. This should be viewed as a vector in itself, such that any linear combinations of such objects is another vector. Suppose one particle is in state psi A and the other psi B. Since the two particles are identical and can only be distinguished by the states they are in, this second expression should be equally valid. Therefore, we should not favor one over the other, but put them in a superposition with equal probabilities. This relative phase is yet to be determined. Psi AB, defined like so, should describe two identical particles, with one in state psi A and the other in psi B. This should be physically equivalent to the case where one particle is in psi B and the other in psi A. A purely notational difference, which is just switching between A and B. We can factor an overall phase, which should have no physical significance. The two states ought to be physically equivalent. This means these two relative phases are equal, which implies thus the relative phase factor, EI alpha, can only be either +1 or -1. Note that this state may not be normalized, but that's okay. Let's label this state according to the relative sign. This definition implies whenever we switch A and B in the state, we simply get back the original state multiplied by its sign. This result should hold even for more than two identical particles. Whenever we consider switching the states of any two particles, the same argument follows true. We notice something striking for the case with the minus sign. Whenever the two particles are in the same state, for example, state psi A, this two-particle state is 0, which means it is invalid as a quantum state, since it cannot be normalized in any way. For this category of particles with the negative permutation sign, no two particles can occupy the same state. This corresponds to the fermions. And for the category with the positive sign, there is no restriction. Any number of particles can be in a given state. These are the bosons. Thus we see how the statistics of identical particles follows directly from their quantum description. One important point we forgot to mention is this. A particle can only be either a boson or a fermion, but not both. To see this, note that the superposition of quantum states must result in another quantum state. So if the plus states and the minus states are both available to a pair of particles, this means they can also be in a state that is the superposition of these two types of states. But such states are not allowed for identical particles, because it has no definite symmetry or anti-symmetry under the exchange of two particles. So a particle must either be a boson or a fermion, but not both. What about composite particles? How do we decide whether a composite particle is a boson or a fermion? By using the permutation rules for the elementary particles in its composition. For example, if we permute two pairs of fermions, we end up with a pair of negative signs, one for each transposition, resulting in a positive sign, in other words, a boson. This means one pair of fermions is like a boson. In general, an even number of fermions behaves like a boson, while an odd number is again a fermion. And the fermions in the composition do not even need to belong to the same species. A hydrogen atom with one electron and one proton, both are fermions, is a boson. Another thing we would like to point out about this state is this. Compare this with the famous Bell state in the EPR-type experiments. With one particle spin up and the other spin down and vice versa, together in a superposition. This is what is known as an entangled state. These are quantum states in which there exist quantum correlations between its two parts. The details of this are not important here. Just note that quantum entanglement is considered a great resource in the field of quantum information. Note that the two particles in this state are also identical particles. Similar to our state above, at first glance they look like the same type of states. So is this quantum entanglement? Are all the states of a pair of identical particles automatically entangled? Actually, there's more to the Bell state that meets the eye. The first and second cat actually carry additional information about their positions. In an EPR experiment, a pair of particles are prepared in the Bell state and sent in opposite directions. The two wave packets describing them have peaks at two distinct positions, x1 and x2. Rewriting the state to make explicit these additional information about the particles' positions allows us to make a better comparison with the state above. The actual symmetrization or anti-symmetrization to take care of the indistinguishability of identical particles should really be applied individually to each term in the superposition, according to the convention above. As you can see, the Bell state actually involves 4 different single particle states, and therefore is quite different from the state above. So the answer to our question is no, this is not an entangled state. Pairs of particles have to undergo additional physical processes in order to be entangled. Entanglement is not a necessary condition for pairs of identical particles, but every state describing identical particles must have the symmetric or anti-symmetric properties that we are talking about here. Of course, this is not the end of the story. Sometimes, just when you thought a rule should always hold, someone will find an exception. This is the case for particle statistics. It turns out that if we extend the idea of exchanging particles in a more physical way, in some special situations, like in a 2D system, there could be particle statistics that are neither bosons nor fermions, but anything in between. These particles are known as anyons. Its name comes from the fact that under exchange, it is possible for its states to gain any phase other than the plus or minus 1 for bosons and fermions. Strictly speaking, these are quasi-particles, which are collective excitations in some materials. But these particles are far from hypothetical, and have already manifest themselves in the phenomena of the fractional quantum Hall effect. That's a topic for another video. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.